Hello everyone, thanks for coming. If you guys don't know me, my name's Travis. I'm a mentor with 971. I've been with the team since 2005 when I was a freshman on the team, and then I went through with high school and then mentored while I was in college and came back afterwards and have mentoring since 2013 full-time. So been with the team through a while. I've been involved throughout my whole time. I've been involved with mechanical design and kind of been part of the evolution of, as we've been learning kind of how to make robots that are controllable, both from sort of a control side and also from the mechanical side. So Austin, my brother, is giving a talk today about how do you control a robot, how do you go through the math to figure out the algorithms for it, and then how do you write software. And one part he's not going over that is just as important is how do you make the mechanical systems to support that kind of software. And it's not quite, there's a lot of similarities to what people are doing for purely mechanical based systems, but there's some things that kind of you can do to if you pay attention to, will result in better and more controllable robots. So we're going to go through some of that today. I'm going to kind of start out with an overview of sort of what sort of mechanism design can you do if you start with the assumption that you can have control loops on everything. How does that change your design? And then kind of go through some of the mechanics of how do you select your motor and gear ratios, how does stiffness impact the robot, and how do we kind of optimize that? We have one thing we pay a lot of attention to is backlash. So where does backlash come from, and how do we minimize that? And then kind of what are some other sort of mechanical things that you need to keep track of? So these are I guess our last 4 robots. And all of them relied heavily on control systems. And so we kind of start using designing with control systems because one of the things it does is it shifts complexity from mechanical to software. So if you want to do some complicated thing at the end, you could solve it purely mechanically, or if you bring software in, you can kind of do less mechanical and more software. And one of the advantages of putting complexity in software is that it's a lot easier to take a software that worked on one mechanism and convert it over to another. Every time you do a mechanical mechanism, you have to completely redesign it and kind of custom. You can use like components and ideas, but a lot of it is you're doing all the CAD from ground zero again. So and then another kind of advantage that we like is that when you have stuff with a control loop, you have a lot of flexibility designed into your mechanical mechanisms. In order to make it effective, you do need control systems on there, but once you have them, it's easy to kind of adapt and iterate through software. So you don't have to remake as many parts, and that kind of helps you kind of grow with the robot during the post-ship time. And then another nice thing is that as you're using the mechanism, if you were to use, pistons are a good example of kind of an alternative to sort of using a motor on something. With a piston, you only have 2 positions. You have up and down. With control system, you can have up, sort of down. And also another kind of subtle thing is that if something's not the right height, if let's say the balls aren't intaking quite right because your intake height's wrong, you just kind of adjust the number in software, you run it again, and now it's right where you want it to be. So kind of, I guess, if we look at our 2017 robot, we have a hood on there and a turret for our shooter. That was kind of, we said, hey, let's do a shooter hood and a shooter turret, because that way we can kind of delay, we can have more flexibility in how the game's going to be played later. We can shoot from any position. And another thing is that the reason we have a hood on there is that if we didn't really want to go through we did a bunch of testing on what we wanted to have our shooter geometry to look like, but we knew that we wouldn't get the hood angle just right the first time. And we know it's a lot easier to go in software and just change the hood angle and say, oh, it needs to shoot a little higher, a little lower. So kind of gave us some flexibility that way. Same thing with our intake. Our intake goes in and out. I think we had like 3 or 4 different positions that the intake would go in at. We didn't really know what those positions would be going into the season. We knew we needed to be far enough out to intake balls, and we knew we needed to stow. And then kind of as we brought the robot up and learned about the challenges, we were able to kind of add in different capabilities to tune that in. If you look at our 2016 robot, we knew we wanted to go from being short to tall, and kind of the easiest way to do that was to put that we came up with was to put some mechanisms in there. So we have 2 joints. We have a shoulder joint and a shooter joint, and that's not something you can really do without having control systems in there. Kind of the whole mechanism of it unfolding was rather complicated, but from a mechanical perspective, it's like 2 gearboxes and some structure in between them. So yeah, and then 2015, this one was a little silly, would not recommend it again, but we wanted to be able to set the stacks down and have a motion where we thought it was very important to be able to set the stacks down without tipping them at all. Turns out that wasn't important. We missed on the prototyping and stage there. But once we had that design spec, we solved it with a mechanism. You kind of have to watch the video to understand how it fully works. But we had 2 degrees of freedom, and we could lift the stack up and then push it straight out. And that was done via software coordination between 2 joints. Have an elevator up here, and then an arm here. And then one of my favorite applications of controls, leading to good robot design is our 2014 robot. And here we knew we wanted to be able to intake the ball, and so we knew that we wanted to have like a position. We wanted to have a claw that we could move up and down. And then we also wanted to be able to clamp on and unclamp the ball so that we could grab it for intaking, and then when we were shooting, we thought we wanted to open up a little bit. So we could have designed that so we had one claw, so we had just one claw that went up and down, and then it had a piston or something that would open the top of the part of the jaw just a little bit. We instead decided to put one motor on each the top and the bottom, and this meant that we could adjust. First of all, we could adjust how much we clamped when we shot, and that was really helpful because we didn't know how hard we wanted to clamp the ball when we were shooting. Like, how would that impact accuracy? What would be the optimal place there? And then there's a lot of other things that we were able to do that we didn't even think about that were really nice. So one of the things is that when your ball was bouncing down the field, it was really hard to get a hold of it. We were able to open the separation distance between these 2 claws so we could go up, and then we could go and we could clamp down on the ball, kind of catch it out of the middle of the air. That wasn't something that you would sit at the beginning of the season and say, hey, that sounds like a great idea for a robot. It wasn't an obvious thing to do. But once you had a robot that could do that, you're like, oh, this isn't really working well. What if we just took the top claw and opened it up? And that's kind of like, that's the sort of iteration that you can do if you have a flexible control system. So if you look at kind of every problem that you're solving with controls, you could also solve with mechanical. So there is a choice there. This is, as I was mentioning, both are successful robots. They had similar problems to solve, and they just chose to solve them in different ways. So here, intake moves up and down with a piston, and here we just took that piston and we replaced it with a motor. And as I mentioned, this kind of gives us flexibility for sort of what we could, for us, this was the simpler one to do. It took less mechanical design, and we didn't have to think through all the integration and the packaging as much up front. And it gave us flexibility that we enjoyed using, of being able to adjust the position of the intake. And I think we had different modes. When we were going under the low bar, we'd put it extra far down. And when we were shooting, we held it out some. And when we were stowed, we held it back. So we took advantage of that there. So one of the first things when designing a mechanism, once you have the sort of idea of, this, we want to have let's say we'll use the simple case of an intake arm. We have an intake arm that's going to go up and down. One of the first steps is kind of figuring out, after you figured out like what it's going to look like, figuring out what your ratio is and selecting it. So motor selection has gotten really easy these days. Basically use a 775 Pro for everything. So this motor is really lightweight. It has a great power, a lot of power, so it's great power to weight ratio. Also, the motor, so kind of the 2 motors that we use are 775 Pros and Sims. Sims are a lot heavier than 775 Pros, but they have a lot more thermal mass, so it's harder to burn them out. We've found that you can use a 775 Pro and not burn it out, and if that's not enough, you just use 2 of them. So this is a plot. I don't know if you guys are familiar with it. This is from the VexPro website. This is a great plot to understand. What they did is they basically took a lot of different motors, and they put them in a fancy device called a dyno, which is a thing for measuring torque of a motor. So they did what's called a lock rotor test. They took the motor and they clamped it so that it wasn't going to spin. And in between that clamping stage, they put a sensor in there that measures how much torque. And then what they did is they applied different voltages to the motor, and they saw what happened. And they measured the amount of torque as a function of time. So the torque, you'll notice, like at 12 volts, starts off really high, and then it goes down. And at 10 volts, it starts off lower, and then it goes down a little bit later. And you notice that around 4 volts, it starts off not as high, but it kind of lasts, it goes off and steadies out to here. So what's happening when this goes down to 0? Right here. Anyone? Yeah? Burn out the motor. Yeah. So what are you going to see when this happens? Bunch of smoke, right? So the goal of the mechanism, and you notice it doesn't come back. It doesn't go up, right? So you do not want to burn out your motor. So we're designing our intake arm. We want it to be able to go up and down the whole match, whole competition season, all that. So basically, what we want to do is we want to choose, we don't want to design towards the stall torque of the motor. If we do that, we're going to end up burning it right away. We want to design for a torque, the amount of a torque that's going to let us go for the whole lot match. So you notice this 4 volts line? That one goes on forever. We found from kind of experience that this is a little too, if you design exactly to this line, that's a little too aggressive and you still burn out the motors eventually. So we've designed to a 3.5 volt limit. So basically, so designing the 3.5 volts, that's going to give us how much torque we can get out of the motor for our mechanism. And then we can use the geometry and the dynamic and the statics of our mechanism to figure out, is that going to be enough torque to do what we need to do? So the first part. And so you need to, from the 3.5 volts, you need to calculate out how much torque that's going to actually be. So you'll notice the maximum torque the motor can provide is 0.71 newton meters. But this chart here, this is all at 12 volts. So we already said we're not going to run at a full 12 volts. So what you have to do is you have to get the stall torque, at 3.5 volts, we need to just take the ratio between 3.5 and 12, and that gets us 0.21 newton meters. So that's the torque that we're going to design. We're trying to pick a gearbox that's going to let us lift up our arm with 0.21 newton meters. So to calculate the ratio, we want to figure out what's the worst loading case that we're expecting our mechanism to have. And with our intake, we're not actually interacting with we're going to be interacting with the balls and stuff coming in, but basically our worst loading case is going to be when we have to hold the intake all the way out horizontal. And that's kind of, this is our 2016 intake, and I'm going to use the numbers from it as an example. So we need to figure out what that worst case torque is. So I just went in the CAD model and measured what the center of mass was relative to this axis here and how heavy it was. So the mass of the mechanism is 4 kilograms, and it's 0.26 meters from this axis. So that's going to give us a torque of 10.2 newton meters. So I cheated a little bit because we actually have a full model of what this intake arm looks like. When you're picking gear ratios, you probably don't have this all picked out. So kind of what we would do during the season is that we would say, hey, we want an intake arm that goes up and down. And we would get to the point where we had sketched out what that looks like. We kind of know how long we wanted it to be and sort of the rough CAD sketches of how the geometry is going to package. That'll get us the length. And then we'll have an idea of what's going to go on it. So there's a gearbox here that's a pound. I think each of these were like a half pound. We have 6 of them. So that kind of gets us up. Start adding that up, and you're going to get up to the total weight. So you can kind of take a rough estimate of that. And you just got to keep in mind that at the beginning of the season, it's a rough estimate. So when you get to the end, that number is, you probably want to add a little bit, add what's called a factor of safety on top of that to what your actual ratio is. So in our example, I'm just going to go through with a 10.2 newton meters. And then, so that's 10.2 newton meters at this axle to hold it up. But we said our motor only has 0.21 newton meters of torque. So we're going to have a gear ratio in between there. And if you guys know how gear ratios work, we just take the ratio between those two torques. If we want to we're trading off the speed for torque. And so if we take the ratio between those two numbers, we get that we need a 49:1 ratio in order to hold the intake arm up at that 3.5 volts. So now that we have our gear ratio through our kind of simplified number, let's go and look at and see how that stacks up and sort of as a gut check. So one of the things to check out if is this a reasonable ratio from other perspectives is to kind of look at how long will it take us to move that intake arm up and down, because that's probably something we care about. You don't want it to take too long, and you probably also don't care if it takes and there's a certain threshold of that's fast enough. So looked at what range of motion we need, and that's 150 degrees. And then this is just a simple model, ignoring all of the dynamics. So if you guys remember from physics, if you have a mass that's at rest and you want to accelerate it and then you want to deaccelerate it, you don't just take the maximum velocity and multiply it by how far you're going. That's not going to tell you how long it's going to go. What you have to do is you have to account for the fact that you're accelerating and then you're deaccelerating. I'm not doing that here. I'm assuming that you're going to accelerate reasonably fast enough, and you're going to deaccelerate reasonably fast enough, and you'll be at top speed most of the time. And that's kind of a okay assumption here. And the other thing is that when we get to the number at the end, we'll just keep in mind that that's like that's the best case. That's the fastest that you could ever do it under ideal, like not, or I guess in unfeasible conditions. So we'll just use that as kind of a gauge. So take 150 degrees. So that's 150 over 360 rotations. And then this number here is the free speed of the motor. So if you look at this chart here, this tells you what speed the motor goes at under zero torque. That's down here. That's the free speed torque there. And then converting things around to seconds, and then our multiplying times our ratio. So we get a number of 0.65 seconds. I'm going to get back to that one. That's a little ridiculous. So that means that you could put the arm up and down, I think like almost 7 times in 1 second. That's probably faster than we need. So another check that's good is look at how much force is the intake able to generate when you're at stall. So that's, if you remember back to our discussion of the 3.5 volts, that would be, let's say, at 12 volts. So that's the maximum. Let's say we ended up running into a wall or something, and we're pushing against it, or we've had this happen. Someone put the intake down on the edge of the field. What's going to happen? How much force does it have at the end of the mechanism? So that we know how much. So the stall torque of the motor is 0.71 Newton meters. So the stall torque at the output is just times our ratio. And then to convert from Newton meters to actually newtons, or a unit of force, we divide that times by the length of our arm, which in this case is 0.35 meters. So out of that, we get 99 newtons. I don't really know what newtons mean either. So 22 pounds force of force. So that's probably like, we could probably have an intake with that much stall, but it's a little on the light end. We kind of, intakes are one of those things that like we don't fully know what all our intake is going to run into. So it's kind of something that doesn't hurt to err on the high side. And another thing to keep in mind is what's going to happen if we do stall. How long can we stall at this time? Someone remember from that chart earlier?
Just a few seconds.
Yeah, just a few seconds, like maybe like 1 or 2. So that's a bad situation to be in. So it's not really, that force is kind of really an upper limit of how much force we could get out. So we got a ratio, then we did a little bit of gut checking on it. And kind of what we have to ask ourselves is, how certain are we in our design inputs? And so that comes back to, I had the full CAD, so I was able to know my weight pretty well. You guys, early in the season, you're going to be making an estimate on that. Another thing is that, an intake, we don't really, we were using the load case of just holding it out. Don't really know if that's, our worst load case. It's a pretty reasonable approximation, but intakes interact with a lot of things on the field. It's probably something, we probably want to have extra room above that. And another thing is, don't undervalue overkilling it. It doesn't, having the fastest intake in the world isn't good if it burns out in some of your matches. So we kind of, in this case, we look at the 0.65 seconds, we say that's way too fast. We don't need a mechanism, even if we could have our intake go up and down that fast, that's too fast. Probably about like 1/3 of a second, or I guess 1/5 of a second is what I did here. It's probably more reasonable. So already we're like, hey, look, we can add more reduction in there just to give ourselves more room there. And then the other thing is that 22 pounds force at the end, that's probably a little low for an intake. So right away we're saying, hey, we're probably more limited by how fast we're going. We just need to pick something that's fast enough. So I just threw on a factor of safety of 3, and that gets us to 0.2 seconds and 66 pounds of force at the end, and 147-to-1 ratio. So, and if we look at what we did in the season, went back and compared the ratio. In the season, we picked a 256-to-1 ratio, and that was actually plenty fast, so probably could go slower if we wanted. But it's important to note that during the season, we kind of started out with a lot higher ratio because we had a lot heavier intake to begin with. So it was kind of less. We could go faster if we wanted. So that's one way to go through a mechanism. And this is a case of a mechanism where the first number that we calculated wasn't closed. It was like, we had room, and we kind of then just backed down to looking at pure speed. I'm going to go through a calculation example on a mechanism that was a little bit more towards the limit. So if you guys recognize this is our our shooter arm from 2016 with the shooter all the way out. So same idea, put it in the worst case scenario. So that's going to be when we're just lifting it up, and if we had the shooter all the way extended out. It's going to have to lift up its own weight. And so did the same thing. I calculated what the mass was and how far out it was, and it was 10.6 kilograms, and it was at 0.59 meters, and that got us that we need 61.3 newton meters of torque to lift it up. So that's a lot more torque needed, and because this is both a lot longer and a lot heavier. We do the ratio on that between the maximum torque that we're designing to. We get to 292 to 1 ratio. So already we're saying, hey, we need a lot more ratio, a lot more reduction on this mechanism. So we're going to go through and kind of check out against the speed check. So here we have 100-degree range of motion because we're going from all the way down flat, just a little bit past backwards. And so if we calculate out the time on that, that's 0.26 seconds. So just looking at that right away, 0.26 seconds, that's a lot closer to kind of what's a reasonable amount of time. We probably don't want it that much slower than that. Because if you think about it, every time you're going to make a shot, it's 0.26 seconds to get the arm all the way up. And that's 0.26 seconds at the best case scenario. So really, we have to add on extra to it. So if we're adding a 50% error margin on that, we're almost up to half a second to get the arm up. And that's actually about how long it took our 2016 arm to come up. It was workable. If anything, it was a little on the slow side. So, and if you look at the numbers that we ran in the season, we ran a 299 to 1 ratio. So that's really close to that 292 to 1 ratio that we just calculated through this simple math. And just to add some data to this, so the 299 or the 292 ratio is with no factor of safety. That's not adding on any fudge factor here. So that correlates with what we saw during the season. During the season, it didn't blow during our matches, but if we were like in the pits or on the practice field practicing and we were taking 50 shots in a row where the arm was going down, up, down, up, down, up, and we were just shooting balls trying to figure out what was going on with our shot. If we shot like 50 balls, we'd get to the end and we blew a motor once or twice during the competition doing this. So in hindsight, the fact that we chose the exact number that we calculated from this, that wasn't a good, we chose a number that was right next to what we calculated. That's not a good idea. We should have added some factor of safety in there. So, looking here and saying, this 0.26 seconds, we really don't want to go much slower than this. We have one of two options. One, we just do go slower and we accept that time penalty and the time delay that's going to come from that. And the other option is that we add in a second motor on that. So what would happen to that? What would happen to that time if we added a second motor? Actually, that wouldn't change the time. Sorry. What would happen to our factor of safety if we added a second motor? Doubles the torque. So the factor of safety, if we use the same ratio, this 290 to 1 ratio, we'd have a factor of safety of 2. Probably would never have blown a motor out that way. And kind of the way we like to design robots is that we shouldn't ever blow a motor. It just takes a lot of time to replace, and it's kind of obnoxious. So in this case, we probably would go and figure out how to put a second motor in this mechanism if we were designing it again. Or if we couldn't do that, we would just add more reduction. So once we have our ratio, we kind of have to pick how we're going to do it. I won't get too much into detail here, but we use a combination of belts, gears, and chains. And we'll talk later kind of about why we might choose the different belts, why we might choose belts versus gears versus chains. But right now, I just want to briefly cover, if you're choosing a belt, how do you make sure that your belt's going to be strong enough and you're not going to break your belt? Chain, you can get away with a lot with chain. We rarely break a chain, but belts are something that it's harder to have some intuition on, and it's a lot easier to end up right next to the factor of safety there. So just kind of the high level of it, this is a chart that I pulled out of the design guide from Gates. So if you're familiar with belts, Gates is one of the manufacturers, one of the leading manufacturers, and they sell a lot of the belts that people use, and their brand of belt is GT2 or GT3 now. So that's kind of that talks about the tooth profile of the belt. And then they'll talk about different sizes of that tooth profile. So West Coast Products sells 3 millimeters GT2 belts, and then they also sell 5 millimeters HTD belts, which is a different tooth profile, but it's very similar. So both of those are covered in this design guideline. I just thought we'd go through quickly looking at, how do you calculate the load rating for running a belt reduction off your 775 Pro. So if you notice on our robots, a lot of them have a belt reduction off the motor to this for the first stage. We like doing that because they're quiet. It doesn't make a lot of noise, and it gives you a bit of flexibility. So kind of the way we're going to calculate this is first we kind of calculate what our load impact is, and then we look at this table and look up what number does it tell us we can design to. So first case on the load, really when you have a motor, the worst thing you can do is stall the motor. So that's going to provide an upper bound to how much torque we are going to be able to deliver into the belt. And you can use that motor stall torque anywhere through the reduction. So if you're putting a belt higher up in the reduction, you just apply the ratio before the belt to figure out what's the stall torque of the motor, what's the torque at that belt when the motor's stalled. And then, so it's not quite as simple as just saying the stall torque. I won't go into the motor theory right now. You can ask your teammates that went to my brother's talk about more of this later. But kind of at if you look into the details, the motor stall torque is rated for 12 volts on the motor. So that's applying 12 volts across the lead, and that's a pretty most of the time that's the most voltage that you're going to have on the motor. But if you take the motor from full forward to full backwards, motors actually generate voltage. So when it's spinning at full speed, it's going to be generating 12 volts, and if you go from full speed to full reverse voltage, you're actually going to end up with 12 volts from the motor and 12 volts from your applied voltage. So you'll have 24 volts, and that's going to end up with meaning that the maximum torque you could see from the motor is 2x motor stall torque. So if you really want to design conservatively on your belts, you can design to 2x the motor stall torque. Turns out that Gates has all of these numbers are for if you're making factory automation or industrial robots or something like that where you want that belt to last forever. Turns out that FRC is really not that long a time. The number of hours on your robots is very small in the grand scheme of what industry designs for. So you can get away with kind of fudging these numbers a little, and you could design to 1x motor stall if you wanted. That's kind of what we designed to. So so the way we use this table is that so that kind of gives us what stall torque we're looking at, so we're going to compare it to, and then we need to figure out what torque they recommend based on this table. So the first thing is I went and I found the table for the tooth profile I'm looking to use. So that's 3 millimeters GT3 belts, and then in here across the top they have what size sprocket you're designing for, and then they have a bunch of load ratings based on what RPM you're running at. Since we're talking about stall, I just went and grabbed the number number at 0 RPM, and so the number of teeth that we're using is we use 12 tooth pulleys. Unfortunately, they don't have 12 tooth pulleys; they only have 16 tooth pulleys. So I just downrated it by the ratio of the 12 to 16. So if we go look in this table, it's 2.606 Newton meters is what's listed here for the 16 tooth. So that's times 12 divided by 16. That gives us 1.56 Newton meters. So that's the maximum torque that we'd want to put through these belts. If we compare that to our 0.71 Newton meters of stall, and we use the 2x motor stall torque, we actually end up with a factor of safety of 1.1. So that's we wouldn't design that into a piece of industrial automation if we wanted to last for 10 years without maintenance. But for the robot, that's actually pretty good. And so that also, that fits with our experience. We've been running these belts for a while, and we've never had a problem with them. So, this is good. I would add that during our intake this year, we used a lot of 3 millimeters belts on kind of between the motors, and actually some reductions beyond the motors. And in the middle of the season, we ended up stripping some belts when we were climbing. So we solved that problem by just putting 2 belts on the same shaft. But when we went and ran the numbers, which we should have done at the beginning, we figured out we had like a 0.6 factor of safety. So that's why it broke. So the math does work out. It's good to check in. So now that you have a kind of a gear ratio that you want to design to, one of the considerations that we think a lot about is the stiffness of the mechanism. So kind of the first question is, why do you care about stiffness, and also what is stiffness? So at the highest level, stiffness is, everything's a spring, and stiffness is basically how far is something going to move under a given force. So with our arm, let's go to our arm example, we're going to grab the motor shaft and we're going to keep the motor from spinning, and then we're going to go to the end and we're going to push on the mechanism, and we're going to see, under a given amount of force, how far does it deflect at the tip. So the reason we care about this is that, at the simplest level, that's going to kind of tell us end effector stability. So how well does your arm hold position? And then kind of another thing that comes in place that's more subtle is that that stiffness is going to limit how fast you can drive your system. So you guys, with a spring and a mass on a spring, if you kind of like shake the spring, you know how it vibrates at a certain frequency? Maybe? Well, yeah. If you take, like, let's say if we take this yardstick, and if we were going to mount it solidly, we twang it, and you see how it vibrates? So this is a lack of stiffness. This is based on the stiffness in our system. And it's also based on what the mass of this thing is and how stiff it is. And it turns out that frequency is related to the square root of mass over stiffness. And basically what's going to happen is, that when let's say this is your arm and you're trying to drive your arm and have it, we'll use our 2016 arm as an example. You're trying to lift the arm up as quickly as possible. So when you get to the end, you don't want your arm to be sitting there and vibrating like this. It's going to be really hard to make shots like that. So what you end up doing is you end up driving your arm slower than the point at which it vibrates. And so that's like the way we get the shaking out of the system is you just raise it slower. So this guy, I raise it up fast and it starts vibrating. That's not good. So what we have to do is we have to go into software and we have to tune it down so it raises up slow enough that it doesn't vibrate. So we picked a ratio that's going to be able to lift our arm quickly, but if we're not careful, we can't actually do that. So this is actually something that happened to us. We designed our 2016 robot. We didn't pay as much attention to stiffness as we wanted to. We turned it on and we're like, oh shoot, it vibrates a lot. We probably should have paid more attention to stiffness. So I'm going to go through and kind of show what that looks like and why we care about the stiffness. And so how we design to it and think about stiffness. So the first thing is, like, where do you look for things that could be not stiff in your robot? How do you think about that? So one of the things is your transmissions. Your transmissions are basically, particularly you have chains and belts in them. The chain is basically a spring. It's stretchy. You kind of notice, if you've used it on your arms, you'll notice that, like on really long runs of chain, it will stretch a lot on you. So that's going to result in stiffness problems. And then you got to look at your mechanical structure. Do you have really long, thin tubes? That's going to give you stiffness problems. Something to watch for. And then the other thing is, how are you mounting things? So I'm going to go through each of these in a little bit more detail. So I mentioned chains are an important factor in stiffness. They're probably one of the largest factors in their stiffness. And so we're going to go through a little bit of math. You don't really need to use this necessarily, but I find that it's good to go through the math to kind of understand, like, how does the math impact the design decision and what kind of like trade-offs does the math tell us are good. So we're going to start with a simple system. This, if you squint your eyes, this looks exactly like our arm on a chain, right, that we have right down here. So here's our arm that we care about. There's a certain amount of torque here, and there's a certain amount of deflection that you're going to get under a certain amount of torque. And the ratio of this is the stiffness of our output, because that's like, if we're going to push on it, how far we push on it with a pound, how far does it move? If it moves half as far, it's twice as stiff. That's what this ratio and definition is. And then that's our output. So how is it deflecting? What's driving that stiffness? Well, we have a sprocket, and attached to the other end of the sprocket is a chain. And the chain, as I said, is basically a spring. So if you remember from physics, here's your chain. F, that has a force. There's amount. Sorry, You have a chain, that's going to have a stiffness. And if you remember from springs, F equals Kx, right? So that's going to kind of, this force and this displacement from this spring is going to translate into the stiffness at the output. So basically we want to figure out how does the torque at the output translate based on the spring at the input, and how does the deflection, the angular deflection at the output, translate into from the spring deflection at the input. So torque, if you remember from physics, it's going to be force times your radius. So that's going to be based on our force in at our spring times the radius of our sprocket here. So angular displacement, that's going to be based on how far your chord length, how far does this move divided by your radius. That gives you the angular displacement. So we can take these two things and we can put them in this equation, and we get our stiffness on the output in terms of our input from the chain. So we get the output stiffness is going to be the ratio of your input force times your radius divided by the displacement over your radius. And if you look here, this number here, F over delta X, that is the definition of the stiffness of our spring, of our chain spring. So we basically can take this and we can simplify it, and we can replace it with the stiffness of the chain, and we get the output stiffness is equal to the stiffness of your chain times the radius squared. So if you step back and kind of look at what the math tells us in the end, this tells us that if we're worried about how stiff our chain is and our sprocket is, one of the easiest things we can do, so we have two variables. We have our chain, the stiffness of our chain, and our radius. What's going to be the easiest way to increase our stiffness of the system? Yeah, increase the radius. So if we double the radius, how much stiffer is it going to get? 4 times as stiff, right? So that's just simple ratios of triangles. The displacement on the output is going to be equal to the displacement on the input divided by our ratio. And then the force, it's the same thing, ratio there, force balance ratio. I guess you in physics solve it through balancing the moments. You're going to get the output force is going to be equal to the input force times the ratio. So if we think about it, this makes sense. As we have a larger ratio, we're going to get smaller deflection on the output, but we're also going to get, I guess we define ratio opposite of probably what I should have defined it. If we have a smaller ratio, we're going to get a larger displacement on the output, but we're going to get a smaller force. So take these two, we plug it into this equation, we get that our output stiffness is equal to the input force times the radius divided by the output force divided by the radius. This is very similar to what we looks very similar to what we came to last time. What we can do is we can take these two terms, and if we put them together, that is basically the stiffness of the input spring. So now we get that our output stiffness is equal to our input stiffness times our ratio squared. So what does this mean in terms of our gearbox design? We have the belt drive on the motor. Should we be concerned about the stiffness of that belt drive? Think about what's the effect of how we have that stiffness there, and it goes through a lot of ratio. What is that going to do to that stiffness on the at the output? Is it going to be, how much stiffer is it going to be? So we're going through the ratio squared here. So if we have a 100-to-1 ratio, that's going to be a 10,000 times stiffer on the output. It's going to be 10,000 times as stiff as if you had that reduction at your output reduction. So basically, whatever we have on the input, if we're going through a lot of reduction, we're probably not worried about it for our stiffness. Therefore, we can not be worried about it. And kind of, what is this? If we look at this in terms of design, this is our 2014 robot. We actually didn't do this for stiffness, but it turns out to work well here. You notice we have a belt here. We have a chain here. So we wanted to have, chain is going to give us high stiffness on this first reduction, and with a large sprocket, we're going to get even higher. Stiffness. We're optimizing for stiffness here, and then we're actually going through a reduction, and then we're using a belt to get from the top all the way down to our motor at the bottom, so we can keep the center of gravity low. So this belt here has, the stiffness of this belt is going to be a lot less than the stiffness of this chain, but because it's going through a ratio, we don't have to worry about it. It's like basically free. So that's a good example of kind of, of using the ratio to hide the stiffness of something that's not as stiff. So another thing, you don't have to worry about these equations too much. The other question is, how does your structural stiffness vary? Like, how do you think about how stiff your structure is? And so kind of similar thing, we're going to look at the equations that kind of govern this and use them to kind of gain intuition from them on how we should be thinking about design stiffness in our design. So what I have here, this is the beam bending equation. So when you get to college, they'll go through how to derive this and everything. But basically the question is, I have a beam of known cross section here. I'm going to be putting some force, and they call that force P here. Basically, how far is it going to deflect at the tip? And then we can take that, and if you remember stiffness is basically the ratio between these two, between the force and your displacement. And you can move it around, and you get your stiffness is going to be proportional to this. So basically, that means the stiffness is based on how long it is. Longer beams are going to be to the third power. So this beam is, if we make a beam that's twice as long, it's going to be 8 times as not as stiff. And then on the bottom, we have this E and this I. So E, that's kind of like a stiffness cross-section number. It's called the second moment of area. And that thing is in turn proportional to that's basically based on what is your cross-section of your beam member. And then I is basically your material thickness. So kind of from this equation here, the most, well, I guess we'll go through what E is first. Sorry. So the second moment of inertia is, actually I had them backwards. E is your material strength, and I is your stiffness of your beam. So it's basically, if from calculus, it's the area integral of your height squared time over the area. So basically, sorry, I should have put a picture in there. So if we have a box like this, and we're trying to calculate the stiffness about the middle, so you take your little area here, and then you have y. So you square the height here, and then integrate it over the area. So you don't have to do these often. They basically, look up in a table what all the common shapes are. And if you look at, for a solid box, it's based on the width of the box and the height to the cube of the box. So that comes, if we look at that, if we want to make a beam stiffer, what we have to do is we have to increase, if we increase the height of it, we get twice as, if we make something twice as tall, we're going to get 8 times as stiff a beam. So that kind of, so basically the geometry there makes a huge difference on things. And then similar thing with a circle, the stiffness of a circle, because it doesn't have a width, is actually just the radius to the 4th. So that's an even bigger kind of trade-off. And then if you want to know how a box extrusion is, turns out you can just calculate the moment inertia of the outside, and because it's an integral, you can just subtract out what the inside is, and that's what this equation is here. So if we go back to this guy, if we're trying to maximize the stiffness of a geometry, the biggest levers we have are actually based on geometry. They're not based on what type of material we have. So that's how long the beam is, and then what the cross section of it is, and in particular, what's that height of the cross section against your bending. So if we look at our ruler here, if we're bending this way, that's a lot less stiff than bending this way. It's about, 4 times as stiff, so 4 times as high as it is this way. So that's going to be 4 to the 3rd. I don't know. It's a lot. And then, so what I did here is I just took those numbers, and then I calculated them across, these are different common extrusions that we'd use. So I referenced everything to a 1 inch by 1 inch by 16th wall extrusion, and we don't actually care about the absolute stiffness of things. We just care about the relative normalized stiffness. And if you look at that, if you just double the wall thickness, you almost get twice as much stiffness. That's but you'll notice that you have twice as much weight. So you actually stiffness to weight ratio, that's not really an effective thing to be doing. What we can do is we can make, and same thing if you make it twice as wide. Really, you start getting benefits when you start making it taller. So if we take a 1 by 2, a 16th wall, and we make it so that has twice the height, we get 5.4 times the stiffness out of it. And if we look at the stiffness to weight ratio, that's 3.5 times what the 1 by 1 was. And if you go all the way to the end, if you start looking at a 2 by 2 by 16 wall, this is the structure, this is the tube that we use most of the time. It's 8.8 times as stiff, and it's 4 times the stiffness to weight ratio. And then I have a column here. This is basically, these numbers, I calculated out the whole thing. These numbers are my kind of rough scaling. So here, here, when I look at a 1x1 to 1 by 16th wall to 1x1 by 8th wall, because it's thin wall tubing, you can kind of ignore how the effect of it being distributed over the thickness of the tubing. In effect, you just have twice as much metal there, so we'd expect it to be twice as stiff. We didn't change the geometry. All we did was add twice as much metal there at a rough. So that's why you expect a rough scaling of 2, and it's pretty close. And the same thing on a 2x1. Since we mostly care about the metal at the top of the material, because that's it's based on height squared, we care about the metal at the top of the tubing. Since it's twice as wide, we basically have, once again, twice as much material, so we'd expect a rough scaling of 2, and that's pretty much what happened. And then same thing when we make it twice as wide and twice as thick, we have 4 times as much material. It's roughly what we see there. And that kind of, and then as you go down to, like, let's say, look at our 2x2, so it's both twice as wide and twice as tall. So because it's twice as tall, twice as tall, we'd expect 4 times. Sorry, I think did I screw something up here? Yeah, I think it should be. I think I might be missing something. But in a rough sense, since it's 2 times as tall, you're going to get 2 to the third. That'll be 8. And then you can look at round tubing too, and this follows a similar trends. And you'll just notice that as you go to the larger and thinner wall tubings, you can get really stiff and really light things. So you'll notice on some robots they have big round tubes. That's one of the reasons. And I guess I should add, like, the difference between round and square tubing is that round tubing has the same stiffness or strength in all of its directions, and square tubing has its strength in a specific direction. So if you know what direction the force is, like on our intake arm, we know most of the force is going up and down, we can make our tube, we can direct our tube to be, stiff in that one direction. If we don't know what the forces are from, our front of our intake is one thing, kind of round tubes might be better there. And yeah, if you notice, if you go from a 1x2 to a 2x1, so this is 5.4 to 1.8. So basically there's a large difference in the stiffness of a 1x2, whether it's standing vertically or whether it's horizontal. So you got to pay attention to what orientation. You need to pay attention to is kind of what the mounting stiffness of things are. So we kind of ended up settling on these 25 millimeter thin section bearings. They're reasonably priced, and they let you use larger diameter things. And as we talked about, larger diameter things are stiffer and stronger. So kind of ended up doing it. You'll see that all over our robots. There's one down here that this guy's on. There's another one up here that this pivot's on. This is a pivot from our 2016 intake robot. This one was kind of a nice. We milled it out of one piece, so we were able to bolt this straight on and have an axle there. And then the other thing we do is that what we end up doing is we end up putting the bearings inside of the tube. And we just make these blocks that have the bearing pressed into them, and we just bolt them onto the inside. We'll use that all over the place. And then here's another example of how we kind of made an axle for something that was just a single piece. And then we've also done things like in 2015, we used a bunch of clamp blocks to kind of clamp onto the axle. A couple of these are made almost on the router, or they could have been made on the router. Yeah, so because our gearbox wasn't mounted very rigidly. So thanks. So if you look here, the gearbox. This is our original bag day picture of it. The gearbox is actually only held on by these 4 1/8-inch pop rivets, but if you notice, the arm has actually a lot of mass on it. So the arm is going up and down pretty fast, and what ended up happening is it ended up shearing all of these bolts really quickly, and then it started then the arm would you could just move it in it when there's nothing really holding it. So this is a picture of our arm after a couple competitions, and you'll notice that design had to get addressed. So you have a bar here where we added some pop rivets in to kind of try to hold it together, and then we added a bolt here, and that still didn't work. So I guess another concern, something you want to pay attention to, you'll notice that our transmissions have gotten mounted a lot better since then. You kind of want to think about how things are mounted and where the forces are going through. And then I briefly touched on this earlier, but I went through all that stiffness equations because kind of based on what we learned out of this 2016 robot. When we started out, we didn't really have that big a sprocket down here, and we had a long arm, and we had a lot of mass out here. And when, as I said, when we turned on the robot, we couldn't really get it to lift up and stabilize within a reasonable amount of time. And if you hit the robot, it would just start vibrating. So we had to address that. We switched out to 35 chain down here, and that's basically all we could do at this point. In retrospect, what we would have done is we would have put in a larger sprocket down there and started with 35 chain. And also kind of based on, in general, based on our experience from this year and basically our experience this year with 25 chain, we're pretty much done running 25 chain on our mechanisms. It just ends up causing more hassle than it's worth. If you really need it for the weight, we probably would have run this one still at 25. But anywhere we can, we're going to start putting 35 chain just as default. Yeah, and also that's also based on 25 chain stretches more easily than 35 chain, and so you'll end up with you have to retension it a lot. And if you run into and it's fine for most everything. It's fine for most of the use cases. The problem with the 25 chain comes when something happens that you didn't expect. Let's say someone puts the arm down against the side of the field and it whacks it in something hard, or you get hit real hard by another robot. That's you get a sudden impulse to the chain, and then it stretches it, and then you have to replace it, and then it's really hard to replace, and it's just all bad. So in the future, I would recommend that you guys do 35 chain as much as possible. So kind of with another consideration with stiffness is what your backlash is. Backlash is defined by the amount of movement at the output without the input moving. So if you guys, do you guys have experience? Have you guys seen backlash in your mechanisms? Anyone? What does it look like? How do you tell that you have backlash in your mechanism? That's positional error. So that's you have friction in your system and you have meshing error. If you're trying to change directions, you go from one side of the backlash to the other. So you don't actually know where the output is based on what the input's doing. That's going to be a problem. And so that just basically makes it harder to control it, and it also introduces end effector error. So if you want to hold your mechanism at a certain height, it's hard to do that if you have a lot of backlash. So kind of what are the sources for backlash and how do we go about reducing them? It's kind of similar things to similar places to stiffness. We have our chain reduction. That's going to have an opportunity for backlash between based on how tight your chain is and stuff. Then when we have our gearbox, we have each gear reduction. There's an opportunity for backlash between the gear teeth, and then there's actually opportunity for backlash in the belt reduction too. And then a big one in FRC robots is the mating between the hex shaft and the gears. And then you also have to think about your mechanical. So we'll go through some of these, so what are our ways of reducing those? So we like using chain reductions as our last stage because you can get relatively low backlash out of a chain reduction if you tension it properly. So a lot of attention and detail goes into how we tension our chains so that we can get low backlash out of them. And so there's kind of 3 different ways that we go about tensioning the chain. So one of them is that you can take the length of the chain and you can just adjust how long the chain is. So your output and your input are fixed, and then you just change the length of the chain in between. So this only works if you have a limited range of motion on your output. So let's say we have, well, this is probably a bad example. If we have a shooter wheel, is that going to work? Yeah, you want your shooter wheel to go spin really fast. So here's an example. We have a midspan tensioner. We have a block in here with some bolts. We're basically changing the length of the chain by tightening it. So if we wanted to go really far, this is going to start going over the sprockets, and we can't do that. So this guy's great if you know exactly how much range of motion you have, and your length of chain allows for, the range of motion is acceptable within the, and if the range of motion that you have is less than it takes for this guy to travel from one sprocket to the other. So this is a great and easy way to do it. West Coast Products sells a tensioner block that we kind of worked with them on. It's a great, simple, easy way to put a tensioner in there. So then another sort of way is that you can have 2 fixed. You can have your output and your input fixed still. But if you have a larger range of motion, you can't put the inside tensioner in there. Instead, what you can do is you can just change the path length of the belt, of the chain. So you can kind of put a sprocket in the middle and just move where that sprocket is. So I'll get into more details in this in the next slide, but this is a mid-span idler. So this is our 2017 intake arm. The intake had to go all the way in and all the way out. There's a lot of chain run that went through there. So we couldn't, well, I guess we could have done a tensioner on the end, but we chose instead to put one in the gearbox, and we just had a slot here, and we had a bolt, and we'd screw that down until it was tight, and then we'd clamp down, and that would tension our chain. And then another one is that you can move one of the ends. So if you can design your structure such that, if you have a closed length of chain and you want to tension that, you can design it so you can either move, the output end and ratchet that up, or you can move the input end. And so here's an example of our 2014 arm. We had a really short chain run, so the mid-span tensioner wasn't going to work. We didn't really want to run an idler in there because there's going to be a lot of force on this, and that can be really hard on the idlers. So what we ended up doing is we put a block in the top of the tube, and instead of mounting the arm directly to the tube, we mounted it to a block, which we then attached with bolts to the top of the tube. And we just basically, you can see 4 bolts up here, and this is a picture of the block there, and we just tighten the full 4 bolts until the chain's tight. Does everyone see how that fits in there? Yeah? Okay. And then here, this is the other side of the equation. This is on that belt on that same robot. We could move the other side of the gearbox. So basically, you could slide the gearbox along the tube. And if you'll notice in this picture, someone is basically taking a wrench, and we're basically pushing on the gearbox to slide it down the tube. And then once it's tight, we clamp it to the gearbox, or to the tube. Does that make sense? Okay. So I'm going to go through sort of the mid-span idler tensioners because there's a lot of details in how to do those correctly, and they're a useful thing to be doing. So we do 2 different styles of mid-span idler tensioners, and that's based on whether we have belts or whether we have chain. Chain, usually there's a lot more force going through a chain system, so you have to pay more attention to that. And so what we'll do on that, so that the chain has more force than the belts, so it's kind of more complicated. They both have kind of similar ideas between them. We'll start with the belt one. So this is our intake from our 2017 robot. And if you look at it, the belt is a serpentine belt. And the belt goes around here and around an idler and then around our motor here. So this idler, you'll see the slot there. That idler just moves back and forth, and that's how we tension the belt. The way you set the tension is you loosen it, you pull as hard as you can, and you tighten it. This doesn't really have any, the disadvantage of this is that it could loosen on you. If you get like a large shock loading, it could loosen, but because the amount of clamping force you can get out of the bolt is significantly more than the loads, this one works out. On the chains, that's not always the case. So what we do is we put this pusher block in there. So the way we tension the chain is we loosen it, we screw on the pusher block until it's to the right tension, and then we tighten it. And that has the advantage of both giving us better control over it, so it's like not as like a, it's not like an effort of force and skill. And then the other thing is that if you get an impulse load, you have the bolt to back up against your block there. So within the clamp itself, first of all, does that make sense to everyone? Okay. So then there's some details within the clamp. One thing we found is that if you have just a slot, if you have a slot and you use just a button head bolt or a small spacer, what happens is that as you clamp down on it, the bolt will dig into the space, it will dig into the slot because your contact area is very low. So we find it's important to put large spacers on everything so you get good, nice area over between the slot and the plate. And then the other thing is that because you have now that you have large spacers on everything, you need to then make sure that you don't contact the outer race and the inner race of the bearing. So what happens when you contact the outer race? First of all, do people know what an outer race and inner race of a bearing are? No, okay. So a bearing, what's the purpose of a bearing? To make something smooth and rotating, right? So you have one thing that's not rotating and one thing that is rotating. So there's like basically 2 halves to it. And basically and then you have balls between them so you get nice low friction between them. So the thing that you have on the inside and the thing that you have on the outside, those are both called bearing races. It's just the term for them. And so we call them the outer race and the inner race based on the one that's on the inside and the one that's on the outside. So why would it be bad if you had something that touched both the outer race and the inner race? Yeah, you'd have friction there, and then it wouldn't be a bearing, right? You'd basically be clamping the bearing, and so that it wouldn't have that spin ability, right? So what we do is to have it not touch the outer race, we'll actually put what we call nublets. We'll just step down the end of the shaft just to make sure that it only touches that inner race. Because you could see that, I think these guys are, this guy you can certainly see, if we didn't have that step down, the outer part of this spacer would touch the outside and the inside. So that's one thing you want to pay attention to. And then another thing is that when you have the bearings, so this is our idler sprocket. We make these sprockets and use them all over the place. We basically took a sprocket and then the hex sprocket, and we bored out the middle to fit two 1/4-inch bearings in them. What happens if you just put if you just take the sprocket is wider than the two bearings put together, so we end up putting this little pocket in the end of it. Can anyone think of why we'd want to put that pocket in the end of the sprocket? It's harder to machine, but it's kind of serves some functional purposes. Why would that be important? So let's think about it. We have a bearing that has the outer race and the inner race, and it has balls supporting the outer race and the inner race. So we're clamping down the middle. What happens if we had a gap between the two inner races and then we clamped it all down really hard? You're going to be pressing the ball bearings into the edges of the bearing. And that's going to basically dent the bearing and bind it up. So you can get a lot of friction from doing that. So we don't really want to preload the bearings like that. We want to be able to really clamp down hard and not be limited by the bearings. So the way we do that is that we just make it so that the two bearings can touch each other flat. And then when we clamp, the inner race of this bearing is touching the inner race of that bearing, and we're getting contact through the steel, and no contact going through the balls. Does that make sense? So that lets us put this shaft, when we put this bolt through, it lets us clamp down as hard as we possibly want, and that gets us the best ability to resist it from moving. So you'll see that here. And then on the belts, we don't need to have a sprocket for the belts because this is what's called a backside idler. It's running on the smooth side of the belt. So what we can do in that scenario is we just run directly on bearings. But one note is that you need to make sure you pick large enough bearings. If you go and you look in the belts, if you look in the Gates catalog, they have a spec in there for the minimum backside idler tension, backside idler size, and that's basically like you don't want to kink the belt by going over too sharp a radius. So we looked that up. I think those are like 3/4-inch bearings for 3mm belts. So, does anyone have any questions about sort of the midspan tensioners? Okay. I guess I should point out as another note. When we look through designs on bearings or setups like this, I find it really helpful to do a cross section through it, so you can kind of look at it, and you can look at how everything stacks up, and make sure that like all of these little details are taken care of. So it's really hard to see these details by just looking at the overall system. You got to slice down the middle and see what's going on there. And that same is true on shafts in regular gearboxes. Yeah. That's a good question. So let's see. So if we had a really long span of chain, the first thing I'd do is I'd see if you could put a midspan tensioner idler in there. So that's the easiest. This guy is the easiest tensioner to do. You don't have to do anything fancy here. You just have two sprockets, and it's really easy to adjust. So failing that, one of the things you want to do is you want to look at what direction are you expecting loads, the predominant load case to be in. So let's say if you have an arm, it's probably going to take more force to lift it up because you're working against gravity than it is to go down. So so you want the side that is on the tension side, the side that's lifting it up, to you want to put the tensioner not on that side. So that's one thing we'll do. We'll put it on the other side, and then it's just a matter of where does it fit in well. So in that case you want to look for if you want to integrate it into your gearbox, it makes sense to put it in the gearbox side. But it doesn't really matter. If you're long span, you could put it in the middle, you could put it in the far side, you could put it on the close side. If you're doing a midspan idler, it doesn't really matter there. I guess if you look at this guy here, so it's kind of hard to see here because we didn't model it this way, but we have a midspan tensioner on this guy. There's a sprocket here that's in a slot. We have a pusher bolt that pulls it up this way. And if you look at this system here, we expect the main force to be working against gravity, split out. Because you're machining this from one piece. You can take the opportunity to integrate some features into it. So because you're on a CNC mill, it doesn't really add much cost. So in this guy, we integrated in a spacer in the middle. Same with this one here. And then, I should note that, the spacer integration is nice. And then from sort of like a design perspective, the way to make this work out is to make sure you design it with how you're going to machine it in mind. So what we do is we use this vertical collet block. This is a part number off McMaster, if you want. Everyone, you guys know like the 5C collet system on the lathe. You guys familiar with that? So what this guy does is this takes one of those collets and it allows you to hold something vertically on the mill. And this is designed, machined so that it's going to hold it pretty straight vertically, well enough that you could use it for a shaft. So what we do is we take this guy and we plan on holding our shaft upright. We machine one side of it with a relatively long end mill. We designed for a 2-inch long, half-inch diameter end mill. And we design it so we just machine one side, we flip it over, and we either hold it by the middle. So that's kind of sometimes why we'll integrate a spacer in the middle. So we either hold it by the middle here, or we'll hold it by like just a hex or something like that. So we take it, we design it, 2 sides, 2.5-inch long end mill, which means that all of these shafts are under like 3.5 inches long. So that's the first. So that makes it easier. That's one of the design constraints for machinability. And then the other thing is that we designed to start from 7/8 precision ground 7075. All the shafting you buy is made out of 7075 aluminum. So we buy precision ground 7075, and the precision ground just helps us get good indexing from one side to the other, and that you can get on McMaster. So it's takes a little bit more machining. If you guys have a CNC mill in shop, we find that this is relatively straightforward to do once you get the hang of it. And yeah, I should add that doing this is not the only way to eliminate the backlash on your hex. You can try to shim them out, or you can try gluing them, or other things. We just found that we tried shimming one of our robots, and it just took a lot of work, and it was easier. If we'd spent the time up front and just machined all the shafts, it probably would have been less time spent overall. But I know other teams have had success doing that. Does anyone have any questions on these shafts? You can also kind of look through our CAD if you want to see sort of different designs on them. And then mechanical mounting is important. So if your sprocket, the way you bolt your sprocket on, wobbles or gets loose, that's going to be bad. That's going to result in backlash and air, and it may not actively wiggle on you. It may be that it just goes. There's a little bit of friction. It goes from one side of the holes to the other as you're using it, and that's going to result in probably your calibration changing. So pretty simple to fix that. Turns out that bolts are really good for holding things in tension. They're not good in holding things in shear. So do you guys know what the difference between shear and tension are? No? Yes? Okay. So tension is when you're pulling things apart. Shear is when you have two things and you're trying to slide them between each other. So shear would be if we took the sprocket and we tried to twist it, those bolts would all be in shear. Does that make sense? Yeah? So we want to have bolts because we need to hold the sprocket to the tube, but we know that they're not good at doing it in tension, doing in shear. So what we do is we introduce another thing called dowel pins. How many of you have used dowel pins on your robots? You'll find them, they're just a pin. They're often shiny because they're precision ground. So they make them to a really specific size, and that lets you, when you're machining, you're able to, if you machine a very precise size hole, you're able to get a good fit. So the way you, how do you guys machine, do you know how you machine precise holes? Do you drill it, or do you use something else? Look up reamers. They're basically like precise diameter drill bits. So if you want to have a hole that has a nice, particularly if you're pressing it through a long section of metal, if you drill a drill bit, they generally drill oversized. So if you drill a half, or an 1/8-inch hole and you're trying to put an 1/8-inch dowel pin in, it's probably not going to be a press fit. So what you do is you drill a hole undersize, and you take a reamer, and it precisely sizes it to the exact fit. So we use a lot of 3/16 dowel pins. It's convenient because if you take the Vex Pro sprockets, they have a bolt pattern here to be used for bolting it on with their Versa key. What we do is we just drill and remount. We just remount these holes. They're number 8, so they remount to 0.1875 really easily. And then we machine our other parts the same, and we just press the dowel pins in. So that gives us a nice strong connection there. Yeah, and that's kind of important to mounting the sprockets on. Anyone have any questions about the dowel pins? And then I should add that belts and gears do technically have backlash in them, but often it's not the main culprit in our systems. If you go look at our robots, you'll be able to feel some of that gear. What you feel in the backlash on them, it's mostly gear backlash. That's what's left by the time we tension everything and put the hex in and stuff. But it really doesn't. It's not enough to be worried about. It's in the amount of work it takes to get rid of this backlash is a lot. So we just go with gears. So belts are better in backlash than the gears, and the reason for that is that if you have something where with gears you have these guys are sliding on these guys, or one gear is sliding on the other. Anytime you have two things sliding, if you have no clearance between there, is it going to slide? There's like basically if you don't have any clearance, it's basically called jammed, right? So we want our gears to spin, so we want some backlash in our gears. So that's to be expected. And belts have backlash, and that's basically as you move them, the fit between the teeth on the belt and the teeth on the sprocket aren't exactly the same. If you go to the Gates manual, you can look up they have positional error, backlash between different profiles. You notice that there's some profiles that are better backlash than other, but by and large, you don't really have to worry about it. But it's just good to keep in mind that they do have some backlash, it's just a lot less than everything else. And then those are the sort of high-level design, the main design architecture questions. There's a couple other details that are worth paying attention to. This is one of those things that we always forget, and then always, it's hard stops are one of the details that kind of hard to design in right, but they're really helpful if you can get them in there. So a hard stop. This is our arm from 2016. Basically, when the arm went all the way up, we needed something to stop it, or else it was going to run into our top of our superstructure. That wasn't the best idea. So we put in, what we have is we just have a spacer on that gearbox. We mounted that spacer in as rigidly as we can, and then we have a block that hits across it. The purpose of hard stops are to protect the robot from damage. We often haven't had them, but we've tried to put them in as we've kind of learned more. There's a list of some of the hard stops we've had that are not good hard stops. So in our 2014 robot, our Robo Reel was the thing that would, if the claw freaked out and went down too far, it would actually poke through our Robo Reel. Probably wasn't a good idea. We spent the whole season, we didn't do it, but that just adds risk to your season if that's what happens. 2012, we had an arm motor, so when our arm went up all the way, it would hit the motor, or I think it was when it went down. I can't remember exactly. Either way, it would hit the motor, and it actually did this a bit, and we actually bent the plate that the motor was mounted to. Probably not a good idea to have the arm hitting our motor as a hard stop. Probably would have been easy, would have been good to invest in something and have a stop somewhere else. And then 2016 robot, when you opened it up, there's really no way there's nothing that stopped the arm from going too far back other than that chain tensioner running into the sprocket. So if you remember me talking about on limited range of motion things, you would have the mid chain tensioners would run in the sprockets. Well, that was our hard stop. Probably not the best hard stop. We should have done something else on that. And then another one that's kind of a common thing that is a problem on a lot of robots. I guess some of that 2016 included. We have our wiring ends up as our hard stop. That's not a good thing either. You don't want the wires to take all that load there. So just something to keep in mind. You don't have to do it. You can go a season without taking advantage of without paying attention to hard stops, but would recommend not doing that. And then, we're building the systems to be controllable so that we can have control loops on them. It's important to keep a track of where do you put your sensors and what sensors do you put on. So the software people on the team should be driving the fact that what sensors, the people doing the controls and the software should be driving what sensors they want. So work with them on that. But basically, you have two problems that you want. You want to be able to tell where the mechanism is, and you want to be able to tell, you want to be able to tell where the mechanism is within its range of motion, and you want to be able to know like how far it's moved as sort of relative position. So that's relative position and absolute position. And so is an encoder a relative sensor or an absolute sensor? Are you guys familiar? Used encoders before? Yeah? Are they relative sensors or are they absolute sensors? What? Relative? So what happens when you turn the robot back on? Does it know where the arm is based on the encoder? No? Not getting a lot of no's. So it doesn't know where the arm is. Do you guys know how an encoder works? Like kind of what's the core mechanism in there? Yeah? What? Okay, so that's one type of encoder. Yep. They have a magnet, and you can tell they measure the magnet, like how the pole is oriented, and they can tell where the magnet is within one revolution. So actually, that guy is kind of interesting. It's sort of relative, sort of absolute. You know where you are within a revolution, but you don't know which revolution you're in. So if you put it near the motor and it takes like 1,000 revolutions or 100 revolutions to get from one side to the other, you can't know exactly where you are, so that's not sufficient enough. What's another encoder technology that people use? Optical encoders? Does anyone use optical encoders? No? Yeah? So some of you probably have. An optical encoder basically has a disk that has a bunch of slots in it, and you just count the slots as they go by. So that's how it can tell precise relative position, but that's not going to be an absolute position. So in order to control it, you need something to give you very fine resolution of how something's moving, because you need to be able to sense that. So what you do is you put an encoder on there somewhere on the system, and you try to put it as close to the motor as possible. So how close you can get it, and that's so that you get as many counts as possible, because that gets your controls guys as more options there. But you have a problem of you have to stay within the number of maximum counts of how fast the RoboRio counts. I don't know what that is. I just asked the software guys. I'm like, how fast can we go? And they tell me. So you can ask them. There's a number of like how fast the RoboRio can count things, and if they don't know that, they can ask our programmers. So that's like once you have an encoder on, you're going to know relative position, and so in this picture, here's our encoder there. And then the other problem is zeroing. So that's when you start up the robot, you want to know where the arm is, so you don't run into the hard stops or run into the not hard stops. So there's two strategies we've done on that. Sort of the simplest one is using a Hall effect sensor. Has anyone used a Hall effect sensor or know what those are? What's a Hall effect sensor do? It senses when the magnet goes by it, right? Yeah. So that's a great way. It's basically like, I guess, a Hall effect sensor is basically like a switch, like a little touch switch, but has the advantage that there's no moving parts in it. So in the rough world of FRC, it's a lot harder to break. So what you can do is, and this is an example of Hall effect sensors. These are actually 3 Hall effect sensors here. What we did is we put some magnets on this sprocket. We put the magnets so that we had 3 magnets. One magnet would trigger if it went all the way down. The other magnet would trigger if it went all the way up. And then the third magnet would trigger if it was in the middle. And so what we did is we just had it move until it saw one of the magnets. What happens when you see the magnet? Do you know where you are? Yeah. So in software, what they'll do is they'll say, okay, move until I see magnet. Oh, I saw a magnet. And then you know what magnet it is. And they say, okay, great. That's angle whatever. So that's one way to zero. Do you know where you are before you see the magnets? No? Okay. Yeah, that's kind of one of the problems with this system, where the limitations. It's really easy to set up, and it's easy from a software side, but you don't know where you are in between. This was fine for us until we got to 2015. 2015, if you remember, we had the elevators, one on each side of the robot. They weren't actually connected via mechanically. That's an example of using the controls to your advantage to not have to do mechanical work. So because they weren't connected mechanically, we had to home them we had to zero them without ending up with one moving faster than the other and like wrecking the whole system. So what we did is we moved to a potentiometer system. So does anyone know what a potentiometer is? What's it called, a pot? Yes. Yeah. So there's a coil of wire or something like that has resistance on it, and you basically have a wiper that goes over the coil of wire, and where you are on the coil of wire changes the resistance of the measured resistance of the potentiometer. So it's basically a variable resistor based on rotation. So you can use that to tell the angle. You can also get potentiometers that go through multiple angles. So we have like 10-turn pots and 5-turn potentiometers on our robots. And so we can use that to kind of get a rough sense of where the mechanism is. So the problem with a potentiometer is it's not enough resolution to know it's not enough resolution to control off of. If you look at the signal is a very noisy signal. But you have the encoder, which gives you encoder is good relative position, potentiometer is good absolute position. So you use the two together. And what we end up doing is, remember the sensor you mentioned, the magnet sensor, had tell you where you were within 1 revolution, right? So you can use that, or you can use an optical sensor that tells you, has a precise, what's called an index pulse, which tells you where you are in 1 revolution. And basically you can spin until you see where you see that index pulse, or know that, like, let's say you're at the 0 angle of the motor. Then what you can do, so now you have a rough idea of where you are within the whole system from the potentiometer, and a precise idea of where you are with the motor, with the 1 count from the encoder. You can use the two and do math and figure out, now you have a precise idea of where you are within the whole system. Does that make sense? Okay. So before you do something like this, you need to talk to the software team and ask them what they're planning on doing. So it's a lot better if you get to the end and everyone is in agreement of like, great, we've been writing code, and the code we wrote matches the system we have. They're kind of different levels of code input between the two of them, something that needs to be worked out. So that's kind of how you would pick your sensors and pick where you'd put them. I guess, yeah, just to be clear, this is a potentiometer here. We put it near our outputs, so we matched the number of turns on the potentiometer to how far we expected the output to go, so we didn't exceed the potentiometer. And then further up towards the motor, we had our encoder there. And then this guy is our 2014 robot. We had our Hall effect sensors here, and then we had an encoder on the other side over here. So that's kind of what that looks like. And then this guy actually is our 2017 robot. This had a Hall effect sensor. You can't see it, but it's like on the bottom down here, and then an encoder up there. So that's picking your sensors. And then you also want to mount your sensors well so that you don't have backlash in your sensor. So you could have very low backlash through all your system, but if your sensor isn't held on well, you're going to get same level of hysteresis there, where you turn one way and you get wind up one way, and then you turn the other way and you get wind up another way. So you don't actually know where your arm is. So what we do is we try to, some teams will take like just the wires of their encoder and zip tie it on. We find that's not sturdy enough to be able to hold your sensor accurately. We use a lot of Lexan little brackets here. We make them out of thin Lexan so that they're kind of flexible enough that you can get them to match up with all the holes, but they're stiff enough torsionally that it holds the sensor well. So that's one example there. And then there's another example here. So that's how you hold the sensor. And then another thing is you need to make sure that you have good coupling between the sensor shaft and between the shaft on the output of the sensor and the shaft that you're driving. So in our 2013 robot, we kind of just pressed the sensor into the end of the shaft and said, it's a close enough fit, it'll be fine. We ended up having a really frustrated evening where we were trying to figure out why the shooter kept missing. So we'd drive around for a while, and like it would slowly start shooting lower and lower and lower. We'd re-zero the system, and then we'd drive and it would shoot fine again. And we're like, well, what's going on? And we finally traced it down to our encoder was slipping inside of our mount. That was bad, our encoders. So there's two ways that we've done it. One is we use a set screw. People know what a set screw is? Yeah, you can have, you'll have a tapped hole in your shaft, and you'll have a little screw that you jam in through the shaft to the other shaft. So you can see that, you can kind of see it here. It's hard to tell. But here there's a tapped hole right there, and there's a screw that goes through the outer shaft and holds onto the inner shaft. They're not the best way to hold things together. They're really bad at transmitting torque, so don't do them for like holding a sprocket onto a shaft, but they're not a bad way to hold a sensor on. And then another thing we've done, it's kind of hard to see it here. This is a shaft collar, and what we did is we drilled a hole, same thing, drill the hole into the end of the shaft, and then we just, on the bandsaw, we cut a slit in the end of the shaft. So now the shaft has a little flex to it, and you can put a clamp around the outside. You can clamp the shaft onto the encoder shaft. Does that make sense? We like this way now. We're probably going to be doing this going forward. This is what we've done historically. And then another thing that we sometimes end up doing, like on our shooter wheel here, the wheel itself, so all we had is a single reduction from our motors to our wheel, and the wheel itself has bearings in the middle of the wheel. So there's no shaft that we could drill into the end of to put the encoder in. So we had to mount the encoder somehow. Anyone see how we mounted the encoder here? It's actually a poor picture, sorry. Similar concept happening over here. Anyone see how the encoder is mounted? Here's our encoder here, and here's the shaft there. How are the two coupled? Belt? Yeah. So here's our belt over on this side. The encoder had trouble finding a good picture. The encoder's behind here. So we just glued a belt or glued a pulley onto the shaft and ran a belt over. That's a way that sometimes that's a good way to do that. Anyone have any question about the sensors or the zeroing? This wiring is something that we always forget about until the last minute. Some years we forgot worse than others. It really helps if you can think about that in the beginning. Particularly when you have like a large range of motion that you want the mechanism to go through, wiring can be really, really challenging. And we like to joke around on our team. Wiring's kind of like the mechanical team and the electrical team will, call it a mechanical. The electrical team calls it a mechanical problem. The mechanical team calls it an electrical problem. And that actually doesn't change once you get to industry. They kind of like, it's this no man's land where it's like, it's your problem. No, it's your problem. So it really what kind of ends up falling in, like when you have these mechanisms where you have a lot of complicated wiring, it really falls to the mechanical guys to figure it out. I use our 2014 robot as an example. It's kind of hard to tell, but we have a lot of wires running through to motors on the arm, it took us probably a weekend and a half to figure out how we were going to get the wires from one side to the other. We were very close to getting it put together, and we had it all together, and we're like, oh shoot, there's wires, right? And so that was something that if we had thought ahead about the wires up front, we probably would have come up with a better solution that would have worked better in the end, and taken us a lot less time. If you notice, from our 2014 to our 2015 robot, we put an IGUS chain to manage our wire on the elevator. That helped us a lot, and then we had a little bit better time on the ends, and we've kind of since thought a little bit more about it. One of the tricks is in our 2016, we kind of just run the wires next to the pivot. That lets you kind of move the arm up and down, and it kind of floats there between here. And then you can see the same thing kind of here. We had space for the wire to go there. I don't know. It's kind of hard to it's good, I guess, on wiring, I don't have a strong recommendation on what to do, but just encourage you to think about it early. And also, if you're worried about it, prototype it out. I think in 2016 we might have done some prototyping where we kind of took some blocks and tried to run wires between them while we were designing it to make sure we had room. If we didn't, we probably should have. But yeah, any questions about wiring? Have you guys had problems with your wiring? Anyone? Oh yeah, Will, of course. No? Okay. And that's all I have here, unless anyone has any more questions. Just wanted to add that there are a couple resources that are useful. We have a lot of photos on our website. That's where I got all of these photos were from our website, like throughout the whole presentation. And then our CAD's up there too. And then I like the Gates Power, Light Power, and Precision Manual. If you're using belts, it's a good read. And then all the motor stuff came from Vex Pro. Does anyone have any questions about any of the stuff we went through? Or any questions about things we didn't go through that you'd like to ask? Well, if we don't have any more, that's what we have here. Thanks for coming. And if you have any questions that come up afterwards, feel free to reach out to us. You can go through our contact form on the website. That gets routed appropriately. And be happy to help you guys out. And I guess I should add also that we've worked with some teams on this, but if you guys have questions during the season and want to actually schedule a design review, we've worked with teams during the season where they come in week 3 or 4 when they have their CAD done, and we can go through things and kind of like look through and kind of give pointers based on what our experience, based on how we think things are going to go, and maybe hopefully help you guys help you guys tune the mechanical and kind of avoid some of the pitfalls before making it. We did that when I was a kid. We reached out to 254 and we found that to be immensely helpful to get their input and guidance before we actually made the thing, and something that we're happy to do for other teams. Thank you for coming. And
we are 971.